Hello and welcome to Selection with Sathi. We've learned big O notation for upper bounds. Now let's complete the picture with omega and theta notation. Omega gives us the lower bound, how slow an algorithm must be at minimum. Theta gives us the tight bound, the exact growth rate within constants. Together with big O, these three notations form the complete toolkit for analyzing algorithms. Whether you are preparing for GATE CSE, placements, or coding interviews, mastering these notations is absolutely essential. Let's dive in. Let's start with omega notation, written as a capital omega symbol. Look at the definition on screen. F of n equals omega of g of n means there exist positive constants c and n0 such that f of n is greater than or equal to c times g of n for all n greater than or equal to n0. In simple terms, g of n is a lower bound on f of n. F grows at least as fast as g. Let's see an example. Take f of n equals 3n plus 2. We claim f of n equals omega of n, choose c equals 3 and n0 equals 1. Then 3n plus 2 is always greater than or equal to 3n for n greater than or equal to 1. The plus 2 makes it strictly larger, so the inequality holds easily. Now the most powerful notation. Theta. Look at the definition on screen. F of n equals theta of g of n means there exist constants c1, c2, and n0 such that c1 times g of n is less than or equal to f of n, which is less than or equal to c2 times g of n, for all n greater than or equal to n0. Notice what this means. F of n is both O of g of n and omega of g of n at the same time. That's a sandwich. F is squeezed between two multiples of g. Example, f of n equals n squared over 2 minus n over 2. We claim this is theta of n squared. For the upper bound, n squared over 2 minus n over 2 is at most n squared over 2. For the lower bound, when n is at least 2, it's at least n squared over 4. So c1 equals 1 quarter, c2 equals 1 half, n0 equals 2. Now let's understand how O, omega, and theta relate to each other. Look at the key formula on screen. Theta of g of n equals the intersection of O of g of n and omega of g of n. If a function is both O of g and omega of g, then it must be theta of g. But if it's only O of g without being omega of g, then it's not theta of g. Here's a powerful analogy that makes this crystal clear. Think of big O as less than or equal to for growth rates, omega as greater than or equal to, and theta as exactly equal to. For example, 2n squared plus 3n is O of n squared, it's upper bounded. It's also omega of n squared, it's lower bounded. So it's theta of n squared, the tight bound. But 2n squared is also O of n cubed, technically true but loose. It is not omega of n cubed, so it's not theta of n cubed. Asymptotic notations have several important properties. First, transitivity. If f is O of g and g is O of h, then f is O of h. This works for omega and theta too. It's like a chain. Second, reflexivity. Every function is O of itself, omega of itself, and theta of itself. This makes sense because f is both upper and lower bounded by itself. Third, symmetry. This only works for theta. F equals theta of g if and only if g equals theta of f. Big O and omega do not have symmetry. Fourth and most important for gate transpose symmetry. F equals O of g if and only if g equals omega of f. This means upper and lower bounds are mirror images of each other. If f is bounded above by g, then g is bounded below by f. Finally, let's look at the strict versions, little o and little omega. Little o of g means f grows strictly slower than g. Mathematically, the limit of f of n over g of n as n goes to infinity equals 0. For example, it is little o of n squared, because n over n squared equals 1 over n, which goes to 0. But n is not little o of n, because n over n equals 1, not 0. Little omega is the reverse. F of n is little omega of g of n, means f grows strictly faster than g, the ratio goes to infinity. The key difference from big O and big omega is strictness. Big O allows equality in growth rate, little o does not. Big omega allows equality, little omega does not. Gate rarely asks little o directly, but knowing the distinction impresses in interviews.
Let's work through a formal proof step by step. We want to prove that 3n plus 2 equals omega of n. By definition, we need to find constants c and n0, such that 3n plus 2 is greater than or equal to c times n for all n greater than or equal to n0. Let's choose c equals 3. Then we need 3n plus 2 greater than or equal to 3n. Simplify, this becomes 2 greater than or equal to 0. That's always true. So we can pick n0 equals 1. With c equals 3 and n0 equals 1, the inequality holds for every n greater than or equal to 1. Therefore 3n plus 2 equals omega of n. Proof complete. Now a theta proof, which requires proving both bounds. We want to show n squared over 2 minus n over 2 is theta of n squared. First, the upper bound. N squared over 2 minus n over 2 is clearly at most n squared over 2. So with c2 equals 1/2, the upper bound holds for all n, that gives us O of n squared. Now the lower bound. We can rewrite as n times n minus 1 over 2. For n greater than or equal to 2, n minus 1 is at least n over 2. So n times n minus 1 over 2 is at least n times n over 2, which is n squared over 4. With c1 equals 1/4 and n0 equals 2, the lower bound holds. That gives us omega of n squared. Since we have both O of n squared and omega of n squared, we conclude f of n equals theta of n squared. Here's a gate-style multiple-choice question. F of n equals to n squared plus 3n. Which are true? Option A, f is O of n squared. Option B, f is omega of n. Option C, f is theta of n squared. Option D, all of the above. Let's check each one. Option A, 2n squared plus 3n is at most 3n squared for n greater than or equal to 3. So O of n squared is true. Option B, 2n squared plus 3n is at least 2n for all n greater than or equal to 1. So omega of n is true. Option C, we already know O of n squared. For omega of n squared, 2n squared plus 3n is at least 2n squared. Both bounds confirmed, so theta of n squared is true. The answer is D, all of the above. Notice that omega of n is correct but loose. The tighter lower bound is omega of n squared. This example demonstrates transpose symmetry, a favorite gate trick. Given, f of n equals O of n squared. Question: what can we say about n squared relative to f of n? Apply the transpose symmetry rule. F equals O of g implies g equals omega of f. So from f of n equals O of n squared, we directly get n squared equals omega of f of n. What does this mean? N squared grows at least as fast as f of n. This is a very common gate question pattern. They give you an O statement and ask you to derive an omega statement, or vice versa. Just remember, flip the functions, flip the notation. O becomes omega, omega becomes O.
Let me give you 4 essential exam tips. Tip 1. Theta is the most informative notation. Whenever you can determine both upper and lower bounds, use theta instead of just big O. Tip 2. Remember the analogy. O is like less than or equal to, omega is like greater than or equal to, and theta is like equals. This analogy solves most MCQs instantly. Tip 3. Transpose symmetry is a gate favorite. F equals O of g is equivalent to g equals omega of f. Practice flipping between them. Tip 4. Little o and little omega are strict versions. F equals little o of g means f is strictly slower, no equality allowed. Keep these 4 rules in mind and asymptotic analysis becomes easy. That was omega and theta notation explained with proofs and gate examples. We covered omega for lower bounds, theta for tight bounds, the relationship between all 3 notations, properties like transitivity and transpose symmetry, and the strict little o and little omega notations. For more concept videos like this, download the Selection with Sathi app. Like and subscribe. Thank you.